I am Kokichi Sugihara of Meiji University, Japan. I have been creating various impossible objects, and in this talk, I would like to organize them in the form of a family tree in order to make their relations clear. My meaning of impossible objects is that they are real 3D objects, but their behaviors appear impossible due to optical illusions. This is the outline of my talk. We first consider two types of freedom in interpreting pictures as 3D objects, then review 11 classes of impossible objects I have created, and finally organize them in a form of a family tree. Suppose that we are given a picture and want to understand 3D shapes of the object represented in the picture. We cannot determine 3D shapes uniquely. There are two types of freedom. One is freedom in depth. The object might be small and near, large and far, thick or thin, or so on. There are infinitely many different objects whose projections match the picture. The second freedom is a choice of the viewpoint. When we change the viewpoint from which we see the picture, the set of possible 3D shapes also changes. These two types of freedom are main sources of 3D optical illusions. First, let us fix the viewpoint. Mathematically, there are infinitely many possible objects whose projections match the picture. However, our brains usually perceive a unique shape up to the scale and the distance. Actually, our brains prefer 90-degree angles and are apt to interpret a picture as an object whose faces are connected by right angles. This gap will be clear when we consider impossible figures. This is an example of an impossible figure. We call it impossible because we feel that such an object cannot be constructed. However, we can actually construct real 3D objects. We may have an impression that it is composed of rectangular rods. This is the same object seen from another angle. We understand that the faces are connected by non-rectangular angles. As shown by this example, when we see an impossible figure, our brains try to interpret it as a rectangular object and feel it is impossible. However, if we connect faces by arbitrary angles, we can construct a 3D object. This is the reason why some impossible figures are not impossible. Using the same trick, we can construct real 3D objects from various impossible figures. We call them anomalous objects because impossible figures are also called anomalous pictures. This is the first class of impossible objects. In the next example, the object looks like normal. Let's insert motion. The rod is hard and straight, but can go through the two windows simultaneously. We feel this motion is impossible. The windows look rectangular, but they are parallelograms, so the motion of the rods are not impossible. In this case, the object is unfamiliar, but its projection gives a familiar figure of a rectangular object. So our brains interpret it as a rectangular object and feel the inserted motion impossible. By this way, we can construct various impossible motions. This is the second class of impossible objects. Now let us move to a third class of impossible objects. A single image does not have sufficient information about the depth, and hence we have large freedom in choosing the associated 3D object. This in turn means that we can specify two desired appearances from two special viewpoints. For example, we want an object to appear a flower from the first viewpoint and to appear a butterfly from the second viewpoint. And we can actually construct such object. In each scene, a mirror is placed vertically behind the object, and so we can see how the appearance changes when we change the viewpoint. A flower changes to a butterfly, a circular roof changes to a corrugated roof, and so on. We call them ambiguous objects. This is the third class of impossible object. In the next example, we have two cylinders separated from each other, but they are intersecting in the mirror. The trick is the same as the ambiguous object, but the visual effect is different. Each object does not change in the mirror, but their topology, the wave connection, changes. We call it a topology-disturbing object. This is the fourth class of impossible object. In the next example, a bird is facing to the light. When we turn it by 180 degrees around the vertical axis, it faces to the light again. We cannot make it to face leftward. This object is line symmetric with respect to a vertical line, and hence 180 degrees rotation does not change the appearance. However, we have an impression that the object is deforming during the rotation, and hence we call it a deformable object. This is the fifth class of impossible objects. In the next example, the object itself is almost nonsense, but a meaningful shape can be created by fusing the object and the mirror image. This is another application of an ambiguous object. We call this a reflexively-fused object. This is a sixth class of impossible object. Next class is ambiguous tiling. Tiling is a planar pattern in which copies of a tile covers whole plane without gaps or overlaps. We can construct a tiling that changes to another tiling in a mirror. Here is an example. The tiling of ginkgo leaves changes to the tiling of the maple leaves. We can construct various ambiguous tiling. This is the seventh class of impossible objects. Until now, we made use of the freedom in depth in creating impossible objects. Next, we consider the other freedom, the freedom in choosing the viewpoint. First, we choose two viewpoints at infinity. Suppose that we have a picture on a horizontal plane and see it from mutually opposite two directions, 1 and 2. Then the picture is perceived as two 3D surfaces that are mutually mirror symmetric with respect to the picture plane, as shown by the blue surface and the red surface. One is a height reversed version of the other. This is an example. A picture of a convex surface is placed on top of a box, but in the mirror, the surface appears concave. The red cone is a real 3D object. It indicates the direction of the gravity, which makes the optical illusion stronger. Here are two more examples. The heights of the surface are reversed in the mirror. We call them height-reversing objects. They are the 8th class of impossible objects. The height reversal property can be used in a different manner. Here is an object, and a vertical mirror is coming, but in the mirror the lower half disappears. Actually, the lower half is a horizontal picture because the picture, when seen from the opposite side, coincides with the upper half and is hidden completely behind the real upper half. We call it a partly invisible object. This is the 9th class of impossible objects. Next, we choose 3 viewpoints at infinity. Consider an orthographic projection of a rectangular object. The picture consists of 3 groups of parallel lines. We place this picture on a horizontal plane and look at it in 3 view directions such that one group of lines becomes vertical in the retina. Thus, we get triply ambiguous object. We have an object and its 2 mirror images. They seem all different from each other. The object consists of a horizontally placed picture and a vertically placed flag. This is the 10th class of impossible object. Finally, we can combine triply ambiguous objects with height reversing objects. The triply ambiguous object has 3 special view directions from which we see different shapes. And for each of these view directions, we have the opposite view direction from which we see the height reversed shape. So in total, we have 6 view directions from which we perceive different shapes. This is an example. The object is a plain picture of a rectangular solid together with vertically placed flags. In direct view and the 5 mirror images appear all different from each other. This is the 11th class of impossible objects. We have shown 11 classes of impossible objects. We can organize them in the form of a family tree, as shown here. The root is the left upper corner, and the branches extend towards right and downward. Each branch means that the child node is created from the parent node, and the symbol attached to the branch represents how the child node is created from the parent. The equality symbol means that the same idea as the parent node is created is used to create the child node by changing the way of display. The arrowhead symbol means that the idea of the parent node is extended to create the child node by adding further constraints. The plus symbol means that the 2 ideas are combined to create the child node. The upper 7 classes impossible objects are created using the freedom of depth in various ways. And the lower 4 classes of impossible objects are created using the freedom in the choice of the viewpoint, choosing 2 viewpoints, choosing 3 viewpoints, or choosing 6 viewpoints. This kind of family tree not only makes us to understand the relation among existing classes of impossible objects, but also suggests the further directions of future researches. For example, a new class, which might be called ambiguous impossible motion object, might be created by combining the principle behind the impossible motion object and the height reversing object, and so on. This is the concluding remarks. We reviewed the 11 class of my impossible objects and located them in the branches of the family tree. This tree not only makes us to understand the relations among the existing classes of impossible objects, but also suggests the future directions of our researches. Thank you very much.